Hey, everybody.
Hello, Professor.
Hello, Professor. Welcome.
Thank you. All right, we'll start. We'll start in a second. Let me take care of something real quick. Sci-Hub. I've heard of it. I don't know too much about it though. Is it a place to view scientific papers?
It's actually a pirate website.
Okay.
There's a lot of organizations like Elsevier that charge you.
Yeah,
use their,
Elsevier is a huge ass scam company.
Yeah, so this Russian female researcher, she made this website, and you can basically take any link that's like paywalled, put it in Sci-Hub, and then it'll pirate it.
Nice. That's
Pretty
awesome.
sure it's not legal, but
it's okay. Elsevier is
she's like the Robin
evil
Hood
company.
for researchers.
Yeah, that's great. Okay, so 5:30. So let's go ahead and get started today. All right. Good evening, everyone. How's everyone doing today?
Amazing.
That's good. something good happened.
Yeah, had hot pot with the family.
Nice. Always a good thing. Hot pot is always a fun thing. All right, so it's our last day before spring break, and so it's I know it's everyone's kind of excited to go, and so I'm right there with you. So I'm looking forward to spring break as well. But we got one more lecture to go through, and today this is going to be kind of part 2 of our CFD workshop in SimVascular. And so last time we for the last couple class sessions we've been talking about what CFD is, what are the general steps to running a CFD. And then we're kind of right in the middle of like how you actually run one in SimVascular as well. Okay. And so I think last thing that we did was we assigned the boundary conditions to the inlets and outlets and the walls. Okay. And so where we're going to start today is we're going to set all of these solver parameters right here. Okay. And so we have this kind of big intimidating list to go through. And then we'll talk about what each of these mean, how to set them. And then we'll run the simulation twice. And so we'll run kind of a cheap simulation here on your home desktop, and then we'll run a much more expensive one on the cluster as well. And so I don't think if you've already made an account on the cluster yet, I don't think I've gone through and added anyone yet. And so you guys probably won't be able to run anything right now, but I'll at least show you the what you need to do so that you can kind of do it later. And I'll upload a document that kind of shows you how to actually do this as well. Okay. So are there any questions I can answer before we get started? Okay. And so there's another one announcement I want to make is that there's no I don't have another homework assigned yet. Mostly just because I haven't prepped one yet. But I mostly just because I want you guys to use this time to really get started on your project. So I know several of you have already started with the modeling. You guys have already kind of talked to me and had questions. And so, definitely use this time to, to start the project. Because once we come back from spring break, then, I plan on assigning another homework assignment. So just kind of keep that in mind. Okay. And I think at this point, most people in the class have chosen their projects. But if you haven't yet, then please make sure to do so. So, fill in the Google Sheet for your for which model you want to do, then I can go then I can go ahead and send you the image data so you can get started. Okay. So I think at this point I've caught up with everyone who signed up, at least as of like 3:30 today. And so go ahead and sign up on that sign-in sheet if you haven't already. Okay. Okay. And so let's go ahead and jump back into SimVascular here. And so if you want to pick up where we left off, this is our demo project. Okay. And at this point, what we've done is we've assigned a mesh. Okay. And so this mesh is only 76,000 elements, and so this is kind of small enough to run on my desktop or on my laptop here. Okay. And so we're gonna basically finish setting up the simulation here, and then see how you can actually run it. Okay. All right. And so where we're gonna be is if you're kind of just booting up SimVascular again, is you're gonna go under your simulation tab, and you're gonna open up the simulation job that we were working on before. Right. And so I called mine test job, but yours probably might be something different. Just go ahead and just open that up. And then once you've done that, you're going to go on the right here, and you're going to click on the tab for solver parameters. Okay. And so when you first come in, it might look something like this. And then you're going to click on this tab down here for solver parameters. Okay. All right. And so now we're going to go through this list and talk about, what each of these mean, or at least some of the most important ones. And then, and then from there, we'll be set to run the simulation. Okay. All right. And so the first thing that you'll notice is that the first three settings here, so the number of time steps, the time step size, and the number of time steps between restarts, all of these are blank right now. Okay. And so the reason they're blank is that it's SimVascular is basically forcing you to choose some values for these parameters. Okay. Everything else has default values, which for some cases they work well, but we'll talk about those as well. Okay. All right. And so the first thing we're going to talk about here is the number of time steps and the time step size, right? And so if we actually go back, and so actually let me go ahead and open up our intro to CFD lecture slides. Okay. If you think back to our introduction slides, remember that when you run a CFD like this and you're running a time-dependent simulation, the simulation is going to go one time step at a time, right? And so it's going to solve your solution here at time is equal to 0, and then it's going to move forward in time by one time step, and then it's going to solve the solution here, and then it's going to solve the solution at the next time step, and then so on and so forth. And then the amount of time in between each of the time steps is determined by your time step size. Okay. And so that's the first thing that you should set here is the what size do you want your time step to be? And so that's going to be line number 3 in your solver parameters here. Okay. All right. And so the guidelines the guidelines that you should use when choosing your time step size is that it should be small enough in order for you to get an accurate solution. Okay. And I realize that statement is absolutely not helpful at all, because if you've never run a CFD before, then you don't know what it means to have an accurate solution, and you don't know what small enough means. Okay. And so for that case, I'm going to give you basically a default value. Okay. And so a value that I like to use that tends to work well for most blood flow simulations is 1 millisecond. Okay. And so 1 millisecond is equal to 0.001 seconds. And so if you set your time step size to 1 millisecond, this is usually pretty good. And this is going to this is going to work actually for most simulations. And so kind of like as we talked about for the project, you're only required to do just a steady simulation. But even if you do an unsteady simulation, and even if you do a deformable wall simulation, even then 1 millisecond is going to work well for that. And so this is a pretty good time step size to choose. Okay. And so kind of diving into the theory a little bit, the smaller the time step size, the more accurate your simulation is going to be, right? And so think about a video, right? And so if you're viewing like a video, on YouTube or something like that, generally we expect that a video that has a higher frames per second is going to have a much clearer, much more fluid kind of picture, right? And if you have a higher frames per second, what that means is that there's less physical time in between each of the frames that you're viewing in the video, right? And so it's the same thing here. And so if we have basically 1 millisecond in between each of our frames, that's going to lead to a pretty accurate simulation. Okay. And so, that's a lot smaller of a time step size than like a normal video, but we need that much smaller time step size for CFD. Okay. And so remember, for the time step size, just set it equal to 1 millisecond, and you should be good to go. Okay. All right. And so the next parameter that we're going to set here is the number of time steps. And so the number of time steps basically tells you how many frames or how many time steps that you want to solve your solution for. Okay. And the way that you're going to set this time steps, the number of time steps, is you want to determine what's the ending time that you want for your simulation. Okay. Because the kind of like what we said back here, the total amount of time that you're going to simulate for is going to be the product of the time step size and the number of time steps that you run your simulation for. Okay. And so for most of you guys, since you're solving just a steady simulation, actually for steady simulation, it doesn't matter all that much how many time steps that you choose. And so let's choose the number of time steps to be 100, just so that you don't spend too much time, for the simulation. Okay. And so what this will do is that this will basically have us simulate, 0.1 seconds of blood flow, right? Because we have a time step size of 1 millisecond. And then if we solve it for 100 milliseconds, that's going to put us at 0.1 seconds overall. Okay. And so our simulation is only going to simulate just basically 0.1 seconds of blood flow. But if you're assuming that, everything here is going to be steady, then 0.1 seconds is good enough. And so basically you just, for a steady simulation, you just need to run it for enough time to basically get like fully developed conditions. Okay. And for a steady simulation, these two settings here are perfectly fine for that. Okay. But if you want to run an unsteady simulation, you want to make sure that your number of time steps here captures a full cycle of your pulsatile simulation, right? And so let's say, for example, that your waveform has a period of 1 second, right? And so you want to make sure that your number of time steps here, we set that to 1,000, such that you simulate 1 second of time, right? So that you capture kind of the full cycle. But since we're just doing a steady simulation, we just have to simulate until we reach steady state. And for most cases, that doesn't really take that much time at all. And so we're just going to simulate it for 100 time steps. Okay. Okay. So any questions on this so far? Okay. All right. And so for most of you guys, if you're just going to run a rigid simulation, a time step size of 1 millisecond and 100 time steps, that's usually good for that. Okay. All right. And so the next thing that we're going to set here is the number of time steps between restarts. Okay. And so this parameter here is going to tell SimVascular how often do you want to save your results. Okay. Because remember what we talked about before, that, when you run a CFD, it produces a lot of data, right? And so oftentimes you don't want to save your results every single time step, because that's going to lead to just way too much data for you to handle on your computer, right? And so oftentimes, we basically want to tell SimVascular to only save after a certain amount of time steps have passed. And so, this number right here should be some multiple of your number of time steps, right? And so if we're simulating for 100 time steps, let's say that we want to save every 20 time steps. Okay. And so what this will do is this will save us basically six different snapshots, 5 different snapshots of our simulation results. Because we're saving for every 20 time steps, and we're simulating for 100, right? And so 100 divided by 20 is 5, and so this will have us this will have SimVascular produce 5 frames of output for us. Okay. But you can change this number to whatever you want. And so, if you want to save it more often, let's say that you want to save it for every 5 time steps, that's fine too. Just be aware that, the more often that you save, the more data that the simulation is going to produce, and the more memory is going to take up on your computer. Okay. And so for now, let's keep it fairly modest, and let's keep it at 20, so that we save every 20 time steps here. Okay. All right, and so that's all the mandatory parameters that you have to set. And so technically you can go from here, but there's a few changes that I like to make from the default parameters, just for my own, just because I've had kind of success with these other parameters before. And so, technically the next few are optional, but I've personally had better results doing these things. Okay. And so we're going to skip over most of these other parameters here. And so, most of these are fine by the default. Okay. And so the next thing I'm going to change here is the step construction. Okay. And so explaining what the step construction does is a little bit hard to do without really going into the weeds of CFD theory. But basically what you can think about this is the higher that you have this number, the harder the simulation is going to work on every time step, right? Because what you'll see, and I'll show you this from this when we start running the simulation, for every time step, the simulation is going to work, it's going to work to find your solution, right? And so one way that we can think about it is, for each time step, SimVascular has to iterate a few times in order for you to get to a converged solution. And so the step construction basically defines how often that you want, or how many times that you want the solver to iterate in between time steps, right? Yeah, so you can kind of think of it as like a level of accuracy. And so the higher that you have this number, and so it's going to produce a higher level of accuracy. And so, there's diminishing returns to this. And so, you can't max this out to like 1,000 and expect to get 1,000 times accuracy. So, it's a bit more complicated than that. But basically the idea with the step construction is that you want it to be high enough such that, the solver has enough time or has enough iterations in order to get a converged solution on every time step. And so just from my own personal experience, 2 is a little bit too small for this. And so what I like to do is I like to bump this up to 5. And so in between every time step, the solution can iterate up to 5 times. Okay. But again, I think this is kind of fairly optional. A lot of my own preferences are kind of just formed from my own experiences and my own research. But there's a reason that these parameters are the default, and so you can try both actually. And you can kind of see, and you can see how they perform. And so of course, if you bump up the step construction, it's going to increase the cost of your simulation, and so it's going to make it take more time. But I think that extra time is worth it because it's going to increase your level of accuracy quite a bit. Okay. And so if you want bump up your step construction to 5 because that's what I like to do, but mostly optional. Okay. Okay. Next thing is the residual criteria, and so this residual criteria you can think of it as kind of a threshold for accuracy that you want to specify. Okay. And so kind of going under the hood again, on every time step, what the simulation is going to do is it's going to iterate on the solution. And then each time it iterates, it's going to basically get a measure of the error of your simulation, right? And so that's called the residual. And so the residual basically tells, basically gives you an idea of what the error in that time step is going to be. And so what this will basically say is that, if the residual is less than 0.01, which is about a 1% error, then you're good to move on to the next time step. Okay. And so I like to tighten this up a little bit more too. And so instead of having an error threshold of 1%, what I like to do is I like to take this down to 0.1%. Okay, just to make sure that the simulation is as accurate as possible. Okay. And again, optional. Probably if you don't change this from the default, I think you're probably going to be fine. But this is just from my own experience that I like to do for my simulations. Okay, and so this basically tells it to this residual criteria combined with a step construction basically tells SimVascular that I want you to iterate up to 5 times, and then and during those 5 iterations you should be able to reach an accuracy of about 0.1%. And if you do, great, then you can move on. But if not, then then you might have some issues. Okay, and so these two kind of work in tandem to basically make sure that your simulation is more accurate. Okay, so just for my own preferences, I like to tighten these up to get a more accurate simulation. And so I would recommend that you guys do the same. But I think for your projects, I think it'll be okay either way if you tighten these up or not. Okay. And so, I know that, explaining these things is, it's difficult to do without really going into the theory. But, what I want to do is I want to give you guys a sense of, if you change these parameters, what's going to happen. And so I think, you can get that sense without really understanding exactly what the residual is. And so that's kind of what I'm doing with these explanations here. Okay. All right. So any questions on this so far? Okay. All right. And so a few more things that I like to change. And so, the next things that I like to change are all of these tolerance parameters here. Okay. And so you can think of these tolerances as kind of the same thing as the residual. Okay. And so what I like to do is I like to make sure that all of these tolerances match this residual criteria here. Okay. So I'm going to change all of these to 0.001. Okay. And if you're curious about, what these tolerances are, you can see that they're under this section called the linear solver, right? And so linear solver is basically the part of the program that can solve a very large system of linear equations, right? And so since the SimVascular uses the finite element method, what it's going to do is it's going to produce a very large system of equations. And so, I think, from your linear algebra classes, you might be used to maybe like a system of 5 equations for 5 unknowns, or like maybe, 6 equations, 6 unknowns, something like that. But from finite elements, and I kid you not, and so, what ends up happening, let's say that let's just take an example for like a very coarse mesh like this with 76,000 elements. Your linear system is probably going to be somewhere on the order of 300,000 equations for 300,000 unknowns. And so, that's something that's that's not feasible for a human to solve. And so that's where we really rely on the computer to solve those equations for us. And so all these settings right here are for the linear solver itself. And the reason we have these settings is because once you have such a really large linear system, like once you get into like the 100,000s of equations, 100,000s of unknowns, it actually starts to become really inefficient for the computer to solve that exactly as well. And so what the computer does is it does a lot of approximate methods. So it solves for approximate solutions to that system of equations, just because it's just miles and miles faster than in an exact method. But because you're using an approximate method, you're not guaranteed to get that exact solution all the time. And so what these parameters do is they kind of modify that linear solver to make sure you get a more accurate solution. Right. Oh, question. So can we make some of these changes to the default behavior for future projects? Yeah, definitely. And so, I would definitely recommend these changes. And so, the reason the default values in SimVascular are different is because these parameters are kind of configured to run the simulation on your desktop. And so SimVascular, the general SimVascular user doesn't have access to a supercomputer. And so, we these were configured such that, we run with fairly lax tolerances, and so that your simulations can finish on your desktop computers. But we don't have that issue in this class, because in this class, we're going to have we have a supercomputer, and so we can really crank these up, and the supercomputer can really help us out here. Yeah. Mm-hmm. All right. And so one last thing that I like to change is option 26. Is I like to change that from 1 to 10. And so, that's again, another parameter of the linear solver, and that just makes it so that when SimVascular solves for the solution to that linear system of equations, this just helps it kind of give it more opportunities to solve it, before it kind of exits out. Yeah. So basically, all the things that I kind of just described to you, those are kind of topics that would be covered in like a graduate level CFD course. But this class isn't strictly a CFD course, and so I'm giving you kind of the hand wavy kind of elevator pitch kind of explanation for these things, just so that you can kind of use them and you can change them and kind of know what they do. But if you really want to know what these things are, that requires kind of a really specialized CFD course. All right, and so that's it. And so we're not going to change anything more here. And so just to kind of recap, when you're in the solver parameters page, the parameters that you definitely have to set are everything that's regarding the time steps, right? So that's the first 3 things here. And so you have to set those. because there's no default parameters for that. Okay. And then beyond that, if you want to make your simulation more accurate and, and to have SimVascular work harder, the parameters that you have to change are the step construction, the residual criteria, all 3 tolerances, and then line 26 right here, which is the maximum number of iterations for the NS solver. Okay. And so everything here, these are optional. And so, you can change these if you want. And actually, I would recommend that if you're running the simulation on your own computer to leave these as the default. But if you're going to run these on the supercomputer, then I would definitely recommend cranking these up. Yeah. Was there a question? All right, so just my imagination. Okay, and so now that that's done, we're actually ready to go. Okay, and so now that the solver parameters are done, let's go ahead and click Save Project so that we don't lose anything. Okay, and then now we can go ahead and create the files and run the simulation. Okay, all right, and so you can see here, there's not much left to do, and so from here, what we have to choose here is our mesh. And so make sure you choose the correct mesh. And so make sure you choose the mesh that you created here. So in this case, we used test mesh. Okay. And so after you've selected this mesh, go ahead and click this button right here for create files for simulation. Okay. And then after you do that, then a window will pop up and will tell you that, your SimVascular is creating the files. And then if it's successful, then you should get a notification here that says data files have been created. And so for those of you following along, were you guys able to create the files for the simulation? Okay. I see. So you got an error saying please make sure the pre-solver exists. I see. So that's probably an issue because this SV solver is not installed. And so if you're getting that issue where SV pre is not installed, you need to kind of go back to SimVascular and go to downloads here. Okay. And then you're going to come back to SimTK. Right. And so everything that we're running right now is just SimVascular front end. And so this is probably what everyone downloaded before. And so the other thing that you have to download and install is SV Solver. Right. So SV Solver is the actual part of SimVascular that runs the flow solver. And so, you need to download this and install it on your computer. And I see that they only have the Linux version. So if you're running Mac or Windows, then you have to go to previous releases, and you can download the release from almost 2 years ago. Okay, and so I guess it hasn't been updated in a while. And so if you have Windows or Mac, then you have to download this package as well. And so this is the package that basically lets you create the simulation files and run the simulation. Okay. And so if you're running that issue where the pre-solver doesn't exist, then make sure you download this and install it, and then you should be able to run that. Yeah, you might have to restart SimVascular, and so after you install it, you might have to restart SimVascular and come back, and then you should be able to run from there. Yeah. Mm-hmm. Okay. But for me, I have it installed, and so it's going to take a little bit to run, and so I'm going to go ahead and click Run Simulation. Okay. And when you click Run Simulation here, this is going to run the simulation on your desktop. And so only click this Run Simulation button if your mesh is small enough to run on your desktop. Okay. And so in this case, we're running with the mesh with 76,000 elements. And so I'm going to go ahead and click Run Simulation, and it's going to go ahead and start to run it. Okay. All right. And so if you want to check on the progress of your simulation, you can go ahead and look in the bottom left of the screen. And you can see here that there's kind of a progress window here to let you know how it's doing. Okay. And so you can see right now it's about 1% complete, and it's going to keep on going and keep on trucking until it's done. Okay. Okay. And right now I'm feeling a little bit of regrets because I tightened up all those simulation parameters, but I forgot that I'm going to run this on my computer. And so this is going to take way too long to finish. All right, and so normally if you didn't tighten these up, it would go a little bit faster than this, but you can see mine is going at the pace of a snail. And so let me see if I can stop this somehow. Oh God, so much regrets. All right, we're gonna do the hard fix where I'm just gonna close SimVascular and then open it up again. Will your computer crash if it's too large? It probably won't crash. It'll probably slow it down like crazy because it's taking up a lot of RAM to run the simulation, but it shouldn't crash. I don't think. And so I'm gonna go ahead and close this because it's kind of taking a little bit too long. I'm gonna go ahead and start up SimVascular again. Yeah, so if your computer is not that great, then you can skip this part, and then I'll show you how to run the simulations on the cluster in a bit. But I do want to do one job here on my computer, just so that just so that you can see what the results look like. Okay. And so I'm gonna go ahead and switch all these back to the default parameters. Okay. It's mostly these guys that really struggle. Okay, and so let me go ahead and create these again. Okay, let me go ahead and run the simulation. Okay. Oh, if you have multiple cores on your computer, you can run the simulation in parallel actually. And so I unfortunately didn't do this, but what you can do is you can check this this box right here for use MPI, and then from there you can set the number of processors that you want to use. And so you can set it to as many processors as you have on your computer. And so if you have a quad core, you can set this to 4 processors, and it's going to run in parallel with 4. Yeah. All right, that's better. And so now it's running a little bit faster, and so we can afford to wait for this, while it finishes. And so I guess while that's going, let me go ahead and go to the gateway and approve the people that that have made accounts.
Professor?
Yep. Mm-hmm.
How do you stop the simulation?
Yeah, if you want to stop the simulation, you can open up the so SimVascular opens up 2 windows here, right? So you have the front end, and you have this this kind of terminal. And so if you just close one of them, it should stop the simulation. Yeah.
Okay, thank you.
Yeah. So unfortunately, you just have to stop all of SimVascular, and then that'll stop it. Yeah. Okay. And so here's the gateway. And so you're going to see kind of an admin's look at this. All right, manage users. If only I can sort this by. Let's see. Let's search Fullerton. Let's see what that comes up. Great. Okay, so I'm going to go ahead and I guess these are all the people that made accounts so far. Okay, so let me go ahead and add you guys. All right, so you guys will be under gateway users. All right, so that's Elvis. Okay. Did you install it after you downloaded it? Oh. Are you on Windows or are you on Mac? Okay. Let's connect afterwards, and then I can help you out with that. Yeah. Let's connect afterwards. Okay. All right. So I'll continue adding people in a bit, but the simulation is done, and so I want to show you guys what to do after you run the simulation. Oh yeah. So one more reminder too that just because I know kind of everyone's kind of in different spots, and I'll send an email reminding you of this as well, that everything I'm going over in these workshops, it's documented online as well. And so I'll send people the link for this too. And so if you want to see kind of a text documentation for how to set up and run a simulation, it's here online. Okay. And so I'll send people a link to this just because at least for me, when I'm learning something for the first time, a video is useful. But sometimes I just want to see a document where I can kind of look at things carefully on that. So I'll make sure to send everyone the link for that as well. Okay. Okay. And so my simulation's done. And so, after your simulation's done, the next thing that you need to do is you need to convert your results. Okay. And so what this means is basically, you're going to, this converts the results because right now your simulation results are in kind of a, kind of in a raw output form. And so you can almost think of it as almost like binary files that the solver puts out. And so in order for you to actually view this in a useful format, you need to convert those results from the binary form into a more useful form. Okay. And so the way you do that is you go to convert results here. Okay. And then you might just be able to convert. Right. And so when you click convert here, it's going to ask you, where do you want to put the simulation results? Okay. And so let me go in for this class. Okay. And so let me go select this folder right here. Okay, never mind. Okay. And so in order to convert your results, you have to put in the starting step time, the stop step time, and the increment. Okay. And so to set these, usually for the start time, you're going to start it at time step 0. And then for the stop time, what you're going to do is you're going to input the number of time steps that you put in for your solver parameters. Okay. And so for this simulation, we put in 100 time steps. And so our stop time here is going to be 100. Okay. And then the increment, for the increment, you're going to put in the this setting right here for the number of time steps between restarts, because that's how often you saved, right? And so you're going to put your increment at 20. Okay. And so once you set all those, you're going to go ahead and convert your results. And then it's going to take some time to convert. And then once you get this window here for results have been converted, then you're good to go. Okay. Okay. So was everyone able to? So for those who are still kind of following along, were you able to finish your simulation and convert your results? Yeah, this part's tough because I know everyone's computer is at different places. When running the simulation, did I mention that one core is capable of handling 20,000 nodes? So that's for running on the cluster, and so that basically, if you kind of remember the analogy of preparing 100 sandwiches, and so that's basically just to ensure that each core has enough work to do, and so if you're running, you can do more nodes per core. And so in this case, I had a mesh of 76,000 elements, and I used only one core to do that. And so that's fine. And so it's just going to take that one core to more time to do it. But what you don't want is you don't want to go underneath 20,000 nodes per core, or 20,000 elements, sorry. Because then each processor is not going to have enough work to do, and each core is going to spend more time waiting for work to arrive than it is actually performing work. And so you want to have at least 20,000 elements per node in order to make sure your simulation is efficient. Yeah. Okay. All right. And so I know everyone's kind of at a different spot, but let me show you what you can do once your simulation results are converted. All right, so let me go to that folder here. Okay. All right, and so if you go to the folder where you converted your results, you should see these kinds of files. Okay, and so you should see a bunch of files called all results. Okay, and the file type for this is either a VTP or a VTU. Okay, and so these files are they're basically, you can almost think of it as like 3D model files that you can open up in PairView. Okay. And so, for me, I have it as the default program. But if you just installed PairView, you can go ahead and launch PairView from your computer. Okay. My computer always cries on Tuesdays and Thursdays because it has to run SimVascular, it has to run PairView, it has to run ANSYS, because I teach the finite element class right before this. So my computer works hard on these days. All right. Actually, let's do this. Right, and so now that you have PairView open, what you can do is you can take one of your result files and you can just drag it into PairView. Okay, and so let's take the VTU file. And so if you're following along and you have your VTU files, you go ahead and click and drag this into PairView. Okay, and then you can go ahead and click Apply. Okay, and then what you see here is the simulation results. Right? And so what you're viewing here is the pressure. Right. And so this is the pressure distribution inside your, from the simulation. Okay? And so we've basically simulated, the simulation, and this is the pressure distribution that results. Right? And so the first thing that you should do when you get your simulation results back is you should always check your results. right? And so remember, this is always important that you do sanity checks. And so one sanity check that I always do is I try to make sure that your flow is going from high pressure to low pressure, okay? And so if you remember when we were setting our boundary conditions, this surface up here, or this cap, this was one of the inlets to our model. So this is where flow is coming in. And then, these two legs out here, this is where the flow is coming out, right? And so one thing that you should always check is to make sure that your pressure goes from high at your inlets to low at your outlets, right? And so that basically tells you that the flow is going from here down to here, okay? And so if you have that, then that's great. But if the pressure distribution is reversed, or you're getting maybe some weird values of pressure, then that's something you have to take a look at, and maybe you set something up wrong for the boundary conditions or the parameters. Okay. All right, and so that's good. And so if you want to view different results, the way that you can do that is from this menu up here, kind of near the top left. And so if you're near the top left here, you should see a drop-down menu here. And if you click that drop-down menu, you should see different outputs that you can view. Okay. And so let's view the velocity. Okay. All right. And so the velocity field actually isn't too interesting. It's kind of boring because remember we assumed our walls are rigid, right? And so with rigid walls, our rigid walls are not going to move at all. Okay. And so that's why you see most of this model is blue. Okay. But where you don't see blue here is on the inlets and on the outlets, right? And so this is basically where you have velocities. And the reason for that is, remember, this is where flow is coming into your model. And so, you have velocities here. And of course, the flow has to exit the model too. And so that's why you have velocities here as well, okay? Okay, and so that's the velocity. And so here, let's view the wall shear stress, right? So remember, wall shear stress is something that we're very interested in. And so wall shear stress is something that you can get from the simulation, very, very easily. Okay. And so if you show the wall shear stress distribution, it looks something like this. Okay. And so you can see the areas which are red are areas where the wall shear stress is high, and then areas that are blue are where the wall shear stress is low. Okay. And so you can see here we kind of have this. It's almost like an aneurysm. I've actually been curious for a long time to see if this person has an aneurysm, because this is kind of an abnormal ballooning of this blood vessel here. And so you can see as the flow goes into the aneurysm, we have a low wall shear stress because it's blue here. But then once the vessel kind of tightens up again and it kind of goes through all these kind of twists and turns, then we have higher wall shear stress here. Okay. And so that's that's how you can view the results in PairView. Okay. So PairView is basically your main tool that you're going to use to view your simulation results when they're completed. Okay. Right. And I'll show you one more cool thing, because this is people usually like this, as I'm going to show you how to produce streamlines in your model. Okay. And so PairView actually has a lot of really cool functions here that you can do to kind of modify your simulation results. Okay. And so one thing that you can do is you can kind of trace out the streamlines in your model. Okay. Because right now, when you view the velocity field, you're only viewing the velocities on the exterior of the model, and so that's usually not that interesting. But what we want to see is the flow patterns of blood inside the model, and so we can do that with this stream tracer. They call it a filter here. Okay. All right. And so the way the stream tracer works is that you need to indicate where you want to start the stream tracing. Okay. And so the way you're going to do that is you're going to change the seed type from a line source to a point source. Okay. And so that's going to create a sphere that you can click and drag. And so you kind of click and drag this around. Okay. But I want to start the sphere at the inlet of the model, because that's where my flow is coming in. And so the way you can do that is you can move your mouse over the inlet of your model and then push P on the keyboard. Okay. Right. And so that moves your sphere onto the inlet of your model. Okay. And then typically what you want to do from here is you want to make the sphere smaller such that it only captures just the inlet. Okay. And so the way that you can modify the sphere's size is you can click on the sphere with your right click. Okay. So normally if you left click, you can move it. But if you right click it and click and drag, this modifies the size of the sphere. Okay. And so let me change the sphere to be around that size right there. I think that's fine. Okay. And then let me change the streamline length right here. And so this basically defines how long the streamline is going to be. Okay. And so let me change this from 34, and then let me just make this really big because I just want this to flow all the way out. And so let me change this to 300 right here. Okay. All right. And I know I'm going pretty fast here with this stream tracer just because, you know, I want to make sure I show you the cluster. But you can definitely refer back to this video, you know, to learn how to produce this because it is a cool visualization. And of course, you know, if you know, I'm happy to kind of show you this again too at a later date too. Okay. And so once you kind of set all those settings, we're going to go ahead and click apply. Okay. And then from here, you can see the blood flow patterns inside your model. Okay. And you can see here, the blood comes in right here, and then it basically splits. And then once it's inside that kind of weird aneurysm, it's kind of doing some weird circulation-y stuff. Okay. And then it goes out of your model. Okay. And so this is a way to kind of visualize the velocity patterns or the flow patterns inside your model, you know, in PairView. Okay. Because normally you can only see the outside, but this is kind of how you see the inside here. Okay. All right. So any questions on this so far? Okay. All right. And you can change these colors too. And so, you know, right now you're showing these lines are colored by pressure, but oftentimes it's useful to color them by velocity. And so you can see that, you know, the red strings are, you know, where the blood's going fast, and the blue strings are where they're going slower. Right? And we can make this more dense too, because right now we have basically 100 noodles that are going through. And so let's go ahead and beef this up just so I can show you, because we have a little bit of time. And so let's turn this into 1000. And we have kind of a visualization that looks like this. Okay. Right. And PairView is an awesome software. And so, you know, there's a lot of things you can do in PairView. You know, that it ranges from, you know, some really cool, you know, like engineering calculations that you can do to some really cool visualization stuff that you can do too. Right? And so one thing that I like to do too is I like to change the colors. And so I like to change it because normally, you know, the color scheme is cool to warm, but if you want to change it to jet, which is what I like, you can change it to kind of this rainbowy scheme right here. Right? And so there's a lot to PairView. And so, you know, there's a lot that you can explore in here. And I kind of joke a lot of the times that, you know, and I joke with this with my grad students that PairView is a great software. It's free. There's so much functionality inside PairView, but I think there's no one person on this earth that really understands every single aspect of PeerView because it's vast. There's so many things that you can do with it, and because it's an open source software, you know, people are constantly adding things to PeerView, you know, but you know the problem with that is that when people add things to PeerView, they do a terrible job of documenting it, and so if you try to look up, you know, how do I do this in PeerView, you know, you're going to run into a lot of frustration because the online documentation for PeerView is absolutely terrible. And so the way that people usually learn PeerView is that they become friends with someone who knows PeerView, and then they have that person teach them. Okay, and so that's basically, you know, how you view the simulation results. And so let me go ahead and close this. And so now let me show you how to run your simulations on the cluster. Okay. All right, and so for this, I'm going to go ahead and tighten up this this mesh right here just to make sure that we have enough work here. Okay, and so I'm going to tighten up this mesh and I'm going to make it to be 0.1. Okay, so let me go ahead and mesh this guy. Okay, it's taking longer than I thought. If you're not sure what SimVascular is doing, you can check in kind of the lower left of the screen right here, and right now you can see that it's creating the mesh. I think SimVascular might be mad at me because I closed it down so suddenly before, and so now it's a little bit slow. All right, almost done. All right, refining mesh. Hurry up, please. Okay. All right, and so you can see that we have a mesh here of about 2 million elements, and so that's plenty, and so that's pretty big. And so this is a simulation that you wouldn't be able to run on your computer just because it would just take way too long. Okay. And so actually, now that we're running this on the cluster, let me go ahead and beef these up a little bit. Okay. All right, so this isn't the full thing because I wanted to finish within this class time. Okay. But let me go ahead and bump this up a little bit. Okay. And so let me now go through the same thing we did before. We're going to create the files for the simulation. Okay. And so we're going to create the files, but we're not going to run the simulation. Okay. And so what we're going to do instead is once we've created the simulation files, we're going to upload them to the cluster. Okay. Actually, now that I have some time, let me go ahead and keep adding you guys. Okay. Isaac. Let's see, 1. Okay. Okay. And so if you sign up with your Angelique 16 minutes ago, right? All right. And so if you sign up on the cluster with your Fullerton address, it'll make it easy for me to find you because the only way to search through the users is through name. And so I can do that easily with Fullerton, and then it'll bring up your name for that. But if you don't, you can see that there's a ton of people that have used the cluster. And unfortunately, I can't sort this by created, and so I have to do it by searching for Fullerton. Okay. Okay. And so our data files have been created, and so now let's see how we can run this on the cluster. Okay. All right. And so before we do that, let's see quickly where these files were created. Okay. All right. And so to give you an idea of what the simulation files look like, after you created the simulation files, what you need to do is you need to go to the location on your computer where your SimVascular project is, right? And so in this case, I'm going into the folder for demo project, okay? And so for you guys, it's going to be different. And then once you're inside here, you're going to go into the folder for simulations. Okay? And then inside this folder for simulations, you should see a folder here for each of the different simulation jobs that you have. And so in this case, we're going to go into test job because that's the one that that I just made. Okay. All right. Okay. And then from here, you'll see kind of a big list of files here. Right? So actually, let me go ahead and delete these. Okay. And then these files we're going to some of these files we're going to upload onto the cluster. Okay. All right. And so once you have your cluster account, after you log in, you're going to come to this place right here called the dashboard. Okay. And then so from here, you need to choose an application that you need to run. Okay. And you can see here there are 2 options. And so one is just kind of basic SimVascular. Another is SimVascular using GenVC. And so we're going to be using just classic SimVascular here. This other one, SimVascular using GenVC, is kind of an advanced form of SimVascular. And so, we're not really going to touch that in this class. And so we're just going to use just basic SimVascular. Okay. Right. And so after you click that, you'll come up to this what's called an experiment page. Okay. And so from here, you can give your experiment a name. And so let me give this name SV Workshop. And we'll give it the date. So today's date is 3/25. Okay, 3/25. Okay. You can add a description if you want, but it's optional. And so usually just from the title, it's usually descriptive enough. But if you want to add a description to help you, help you remember what it is, then that's good too. Okay. And so the next thing is going to be the project. And so usually your default project is fine. Okay. And so from here, you're gonna upload the files, right? And so you can see here, it's labeled which files that you need to upload, for which, okay? And so in total, you're gonna need to upload 5 files, for the simulation. All right, and so if you open up your simulation folder, you can see that, you'll have all these files here listed, right? And so the first thing that we're gonna upload here is a file called geombc.dat.1. Okay? All right, and so I'm gonna go ahead and click and drag this, and then drag it in here, and it's gonna upload this file. It's a fairly big file, so I think it was, almost 58 megabytes, and so it's going to take a little bit of time. And so let's go ahead and upload the rest of the files while we're waiting for that, okay? And so the next file that we're going to upload here is called the restart file. And so another file in your folder should be called restart.0.1, and so you're going to go ahead and upload that, okay? All right, and then once it finishes uploading, you should get a, something right here that looks like that, okay? Next, you're going to upload a DAT file. And so the DAT file they're going to upload is called bct.dat that you can kind of see right here. Okay. All right. And so we're going to upload bct.dat. So let's click and drag that there. Okay. Next thing we need to upload is the solver input file. And so that's, that file is right here called solver. Okay. And so let's go ahead and click and drag that up just like that. Okay. And then the last thing that you have to upload here is a file called numstart.dat, okay? And so that's this file right here called numstart, okay? Right, and so for this part of running the simulation, what we're doing here is we're uploading our simulation files onto the cluster, and so that we can run the simulation there, okay? And so there's a total of 5 simulation files that you need to run the simulation. Right? I guess while we're waiting for that, we can talk about what each of these files do. And so this geombc.dat, what this has is basically information on your mesh, okay? And so in our case, since we had a mesh of about 2 million elements, this file is fairly large, right? And so that's why it's taking a while to upload. The restart file basically contains information on your initial conditions. The bct.dat file, this contains information about your inlet boundary condition. Your solver.inp file, this file contains information for all the solver parameters that we set inside SimVascular. Okay, so it has information on like the time steps and all this stuff here. Okay. Numstart, this is honestly, it's kind of a dummy file that's kind of silly that we need to include it, but we also need to include it. And then for you guys, there's there's no optional files that you need to upload, and so don't worry about this. Okay. Okay. And so any questions so far? Okay. All right. And so from here, we need to select the solver or the cluster parameters now. Okay. All right. And so the first thing that you need to do is you need to select an allocation. And so for me, since I'm an admin user on here, I have a lot that's available to me. But for you guys, probably the only thing that's available to you is going to be default gateway user. And so, make sure you select that. Okay. And so the next thing that you're going to need to select is the compute resource. And so you should only have one option for this, which is Expanse. Okay. And so Expanse is the name of the cluster that we're running the simulations on. And so, that's that name. Okay. And then from there, what you can do is you can select the amount of cores and the amount of time that you're going to need for your simulation. Okay. And so at first, it might seem like you can't select anything, but once you click this, you can go ahead and select these guys. Okay. Right. And then from here, you can select, the number of cores and the amount of time that you need. Okay. All right. And so I would say for most of this class, I would say we don't want to upgrade the node count at all, okay? And so what you want to upgrade here is you want to upgrade your core count, right? And so the core count, remember the way that we select this is we take the number of elements in our mesh and we divide it by 20,000, okay? And so in this case, since we had 2.1 million elements, and so I'm going to take 2.1 million, actually I'm going to do it here on the on my computer here, okay? So let's say we have 2.1 million elements, okay? And then we're going to divide it by 20,000, okay? And that's going to give us basically the upper limit of the number of cores that we want, okay? And so in this case, we can run with about 105 cores and still be pretty efficient, okay? And so you can see here from the from this website here that for a typical gateway user, we limit the amount of cores that you can use up to 96. Okay, so let's go ahead and max this out, and let's go ahead and give this 96 cores. Okay, and then from here, and then after you set the number of cores, you need to specify how long you think your simulation is going to run. Okay, and so that specifies basically the wall time that you're going to specify in minutes. Okay, all right, and so for this one, since we're only running 100 time steps, I don't think it's going to take that long. But let's go ahead and just be safe, and let's set this to be 2 hours. Okay. And so I hope it doesn't take 2 hours, because I want to show you guys the results. And so I hope it finishes within the next 10 minutes, but let's set 2 hours just to be safe. Okay. All right. And so this last thing for the total physical memory, you can just leave it blank. And so you can just, we can just use the default memory for that. Okay. All right. And so before you launch your job, it pays to kind of double and triple check everything. And so before you click save and launch, make sure that you have all your files uploaded and they're finished uploading. Make sure that you set your number of cores correctly according to the number of elements in your mesh, and you make sure that you set your wall time to be something that'll give you enough time. Okay. All right. And so now that that's all good, let's go ahead and click save and launch. Okay. And then now the simulation is going to launch. Okay. And so at this point, it might take some time for your simulation to finish. So even though you're running it on the cluster, right? And so, if you want to check on the status of your simulation, you can go back to your dashboard. And so if you check your experiments here on the right, you should see, an experiment for your job right here. And for this one, I can see that it's executing. And so this is the one that I just created. Okay. All right, and so this might take a while, and so let me, we'll kind of wait for this to finish, and I'll hope that that it finishes in time for us to kind of, so I can show you what to do after the simulation finishes. Okay, and so I guess in the meantime, for those of you that are having issues, I guess now would be kind of a good time to see. Okay, and so Melanie, you were having issues with SV Solver wasn't installed, correct? Okay. All right. And so, we're unfortunately, we have to wait a little bit for this to finish. So I guess in the meantime, does anyone have any questions on anything? Okay. Are the credentials the same for the SimVascular gateway? So for the SimVascular gateway, you should log in with your Calstate Fullerton credentials. And so let me go ahead and log out just to show you again. Right? And so when you go ahead and create an account for the SimVascular gateway, you should use this button right here for sign in with existing institution credentials. Okay. And then after you do that, it's going to take you to the Calstate Fullerton, or you should be able to select, Calstate Fullerton from here. And then, it'll, you should be able to sign in from that. And so with that, it'll automatically kind of link to your Calstate Fullerton account. Yeah. Okay. Oh, and the good thing about running things on the cluster is that, once you've launched the job, you can go and walk away and do something else. And so, this is running remotely, and so it's not on your computer. And so you can actually close this window. You can go to YouTube. You can watch J. Kenji Lopez cook some tacos, and then kind of wait for your simulation to finish, right? Because it's not running on your computer, and so you can go ahead and do other stuff, and you can close the tab. And you can just come back when the simulation's done. And so actually, what I did a lot in grad school was that what I would do, like before I would leave for the day, before I would go home, is I would go ahead and launch a job on SimVascular or on the gateway or on a cluster, and then I would go home, eat dinner, go to sleep. And the next day when I'd come back, then I would download my simulation results from there. Okay. And so once the simulation's in the gateway, then it's kind of hands off. And so you don't really have to worry about anything. And so you basically just wait until this says completed right here. Oh, actually, let me see if I can use some of my old jobs here, and let me see if I can show you what to do. Hopefully this is still available because download. Oh, okay, great. It's still here. Okay, and so while that simulation is running, let me do kind of the cooking show thing where I said, in reality, I've already had this thing marinating for the last 24 hours, right? And so after your simulation is done, you should be able to go to your simulation folder or the experiment page, and you should see something that looks like this, right? And so the thing that you want to download here is the tar file, right? And so this is basically a zip folder with all your simulation results. Right? So let me go ahead and download this. Okay. And you can download it somewhere on your computer. So let me download it, put it here, 442, Spring, code, blah. Okay. Right. And so if you've never seen this this file format before, this .czf.tar.gz, this is like Linux's way of zipping a folder, and so that's kind of like their zip folder format. And so you might need something like WinRAR to unzip it. And so if you're unable to unzip it, or if your system doesn't recognize it, you might need WinRAR to do that. Okay. Right. And so let's go ahead and unzip it. Okay. And I actually believe that it's the same, that simulations is the same model as this. Right? All right. And so what you can do from here is that, you can go to your, well, actually, I think I need my mesh. And so let me go ahead and close this. Let me open up a different SimVascular with a different project. Oops. All right, and so after you download your results, you want to return to the same SimVascular project that you created simulation files from, right? And so for this case, I think I created this using a different project, and so let me go here. I think it's this one. Okay, great. Yeah, it is this one. Okay. And so you want to go to the same simulation job that you used to create the files to begin with, okay? And so what you're going to do from here is you're going to skip, all the way down to convert results, and you're going to convert the results from the file that you downloaded, okay? And so, you're going to go to convert results, and then you're going to select the directory where that you just unzipped, okay? All right, and so you're going to click these three dots right here. You're going to go to your simulation results, okay? And then I'm going to go to this folder called proc128, which is the one that I just downloaded. And then inside this folder, you're going to see another folder called 128 procs. Okay, 128 procs case. And so you want to be inside this folder right here. Okay. And then just like before, we're going to set the starting and ending times. Okay, so actually let me do this. Okay. And then you're going to click convert results, same as you did before, right? And so it's going to ask you to for the place where you want to save your results, okay? Right, and it's going to go ahead and work on converting your results, and it's going to take some time because this was a mesh with 4 million elements. I was testing something for this mesh right here. And this one's going to take a while because it was a 4 million mesh, and so just kind of be aware of that you oh, this one's done too. Great. So it was able to finish. All right, but I have this one running already, so I'm going to go ahead and just wait for this one. Right. Yeah, so I'll post a document. I think I have one written for just for showing my grad students how to use the gateway too. So I think I should have one that's that I can just straight upload. Let's see, documentation. Or maybe not. this is not it. No. It's for Jonathan. Okay, so let me. I'll create a document version of how to use the gateway, because I don't think there's a written form for that here. And so let me go ahead and create that document, because I think that'll be more useful to you guys than kind of waiting for these than watching this video, because in this video you can see I'm kind of like fumbling around a lot and kind of waiting for things to complete. So and so I think the document will be good. So let me make that tomorrow, and then I'll upload that onto Canvas for you guys to have as a resource. Okay. But yeah, so that's basically it. And so while we're waiting for this to finish, I just want to show it to you in PairView again. But that's basically, how you run a CFD simulation and how you check the results. Okay. Right. So there are any final questions while we're still waiting for this guy? Okay. Right, and so if you want to see the simulation results for my 4 million mesh, you're welcome to do that. But if not, that's all I had planned for today. So thank you guys for tuning in as usual. And so especially the last day before break, I really appreciate you guys tuning in for that. And so have a great spring break, everyone. Please stay safe, stay healthy, work on your projects, and I'll see you guys after the break.
Thanks, Professor Tran. You have a good one.
Thanks, you too. Thanks, guys. Still.
Professor, I have a question.
Sure.
Not regarding to the course.
Yep.
Actually, I want to just know, do I need the MATLAB for tomorrow comprehensive exam or not?
No, you do not. No.
Oh, okay. Thank you very much.
Yep. Mm-hmm.
Have a good day. Bye.
All right, you too. All right, let's see how we're doing on these simulation results. Okay, we're almost done. Oh, okay, yeah, let me go ahead and approve some people for the gateway while we're waiting. Oh, Daniel, your question, which set image would be the least difficult? I would, if the aorta models are usually not too difficult, especially because it's pretty similar to our it's pretty similar to our tutorial, and so if you want to do an aorta model, that's usually something good. Okay, you might have to restart your computer. I think I kind of remember that, because I remember one of my grad students was having the same issue where, like, he even though after he installed it, then he wasn't able to run the pre-solver, and so you might have to install it, restart your computer, and then restart SimVascular, and then hopefully that'll let you use it. Yeah. Okay. I won't be around for that much longer, and so if you're still having issues with it, just send me an email, and then I can help you with that. Yeah. Mm-hmm. Right. Manuel, did you use your? Oh, okay. Oh, I see. Okay. Oh, Izzy made a lot of accounts. Yeah, I'll be responding to Discord over the break. Yeah, so I'll be available, and so if you want to message me on Discord, I'll be here. If you want to set up a meeting, so I won't have my normal office hours over spring break, but if you want to set up a meeting, then we can do that too. Yeah, just let me know. Yeah. Let me. Izzy made 3 accounts here. Let me see. There you are. Okay, let me give you guys access. All right, there's Manuel's access, and there's Josh's access. Okay, I'll do more tomorrow too. Thanks, you too. All right. Okay, simulation results are done, I believe. Should be, yes. All right, so I actually haven't looked at these. Actually, let me take a look, see what they look like. Oh, that's the VTP. Where's the VTU? Oh, let's look at this one. Okay. And so this is kind of like if you're still around, this is kind of like the creme de la creme. And so if you ran a simulation with 4 million elements, this is kind of the limit that you can do. Right? Okay. Oh, this is kind of an ugly looking model. Why the heck did I use this one? Okay. Oh, what the? Where's the simulation results? That's weird. Oh. Okay, there we go. There's pressure. All right, there we go. Oh man, my computer's really he had to work hard today. He had to do ANSYS and SolidWorks and SimVascular and PairView all in the same day. I'm sorry, computer. Yeah, my computer's he's a trooper. Oh, okay, that's weird. I think it's because this these simulation results I might have misplaced the mesh or something like that, and so I think it's kind of messed up. I think if you and so when you're downloading your results from the gateway and then converting them, make sure you do it in the same simulation job using the same mesh that you used to create it. And so actually, let me go ahead and download the one that just finished. Download here. Close this. Yeah, so I'm oh, even after you restarted, huh? Try creating a new simulation job. And so like from SimVascular, normally we're let me go back to let's see this one. Try creating a new simulation job. So right click simulations and then create simulation job, and then just kind of recreate all the same conditions and everything, and see if that works. Yep.
Do I have to delete the one that I have right now?
No, you don't. You can just leave it there. Just create a new one.
Okay.
Mm-hmm. All right. So let's see. So we're going for 100 time steps, 20. Okay, so let's go ahead and click convert. Let me put this in a different folder. I'll put it here. Thanks, you too. Have a good spring break. Isaac, I got your email too, so I'll look at it after I eat dinner about the heat transfer stuff. Yep. I don't know. I'll have to see what leftovers I have in my fridge. Yeah, I don't think my fiance is picking up anything. I made a teriyaki chicken yesterday, which was really good. It's one of those like very simple dishes, but I really enjoy it because it's you can make it really well.
I made that not too long ago, but I don't think I cooked the chicken all the way, so I got really scared.
Yeah, that's the scary thing. I really like chicken, but like when I cook it, it's always it always worries me to if I'm cooking it all the way or not. And it's hard because because sometimes you don't know. The hardest thing is fried chicken, because like if you're pan frying chicken or something, you can kind of touch it and poke it and see if it's relatively firm and it's cooked. But if you're making fried chicken and the outside's all crispy, then you can't poke it. It's all hard, and so it's impossible to know whether it's done or not.
Yeah, I've definitely ran into that issue too. I got a like a laser thermometer to try to figure out whether or not it's cooked or not, because I'm so paranoid that I'm gonna poison myself.
Yeah. I have one of those like pokey thermometers too, but it's for some reason it doesn't work that well, or I just don't like using it all that much. All right, this one should be good. All right, so let's look at this one. All right, so let's just look at the VTU. Just look at the last time step. Come on, computer, just a little bit more. There we go. Okay, yes, there we go. And so you can see here, for those of you that are left, when I ran it with 2.1 million elements as opposed to 76,000, you could see that this looks a lot smoother. And so you kind of look, if you look back at kind of the recording, you'll see the pressure distribution, but it doesn't look as smooth as this, right? But since we ran with a much finer mesh, you can see the mesh here is really fine. It's like you have an image that's like now in 1080p instead of like crappy JPEG stuff, right? And so the more fine your mesh is, the more the more smooth your simulation results are going to be. And so this looks great, actually. I haven't seen a simulation result this good in a while. So let's look at the wall shear stress. Right? As you can see, the wall shear stress here looks a lot smoother as well, and so that's a good sign. Yeah. Juan, were you able to get it to work when you create a new simulation job?
That's so there's two Juans.
Okay.
That was the other Juan who was having the issue. But
Oh, okay,
not
okay.
me.
Oh, okay, I see. Oh, you're both Juan Castro. That's
Yeah.
Oh, I see. Oh, dang. Okay. Yeah, that's strange. Yeah, thanks. Have a good break. Let me go ahead. Can you send me an email just kind of reminding me about this, and then I'll help you debug after probably sometime tomorrow. Yeah. Okay. Yeah. Thanks for that. All right. I'm gonna sign off for now. All right. Good night, guys.
All right. Good night, Professor. See you. Have a good
Yeah.
break.
You too.